Hello everyone. In this video I'm going to talk about three terminologies or some of them symbols basically that are used in GD&T, and I wanted to explain them to you. So one of them is called control radius, which is basically a radius symbol with a C right behind it. And what is that? It's basically a tolerance zone for a radius, typically a fillet radius, that is between two arcs. One is the minimum radius arc, the other one is the maximum radius arc. And they are like this fillet radius, they are tangent to the adjacent surfaces. So here, if I refer to this fillet and say CR between 16.4 and 6, what does it mean? It means that if I draw two arcs, one with radius of 15.6, the other one with 16.4, sorry, this is 16.4, between these two numbers and this actual machined fillet should be between those two arcs. And more important than that is when it's a control radius, the curve that you get for the fillet has to be a nice and crescent shape. It cannot have flats or reversals, okay? So if it's something like this on the left, that is good, that's a nice fillet. But if it's something like this one on the right, where it has reversals or it can have flat parts, so something like that or something like this, these are not allowed. So if you give something like this, that will be rejected, although it's inside the inside the tolerance zone. And the reason for that is we typically use these fillets to reduce stress concentration. So now if you create something like that, guess what? You're going to get a lot of stress concentration at all of these basically surface variations. So you probably even made it worse compared to if it was perfectly straight like that at angle. Probably this one is no better than that, maybe even worse. So that's why you need to have it a smooth and nice crescent shaped curve, which is between those two radii, okay? So that's the meaning of a controlled radius with two limits. Just wanted you to know about that. The next two things I want to talk about is actual local size, and the other one is called actual mating envelope. What are those? By the way, I just capitalized those letters to match that. So an actual local size is a simple two-point measurement that you do with something like a caliper or a micrometer, and you just check it at one single point, at one single cross-section. So if I give you this kind of barrel-shaped cylinder, which is kind of not made properly, then if you want to check the diameter of this, you can check the diameter here, here, or here, and you might get different numbers, right? So these are all local measurements for the diameter of the cylinder. But when I talk about actual mating envelope, that's a different thing. So if it's an external feature, like a shaft like this, the actual mating envelope, AME, is basically the smallest cylindrical hole that you can put this physical object, this shaft, into, right? That's the smallest hole, the smallest cylindrical hole that will contain the object. So you see, the walls of it are tangent to the high and the low points. And the size of this could be, for example, what? 14.58, right? Or anything else. So that is what we call the actual mating envelope for this physical part. Or another one here, again, you see this kind of bent one has a bunch of local measurements, but again, the actual mating envelope, which is containing the entire object, and it's the minimum size that it can, could be that diameter. Similarly, if you have an internal feature, an internal hole, Then the actual mating envelope is again a perfect cylinder that will pass through this hole. It's the smallest perfect cylinder that will pass through the hole. So you see again, the walls of that are touching the internal points, the highest and the, not the highest and lowest really. Here the closest points basically to each other. So again, if you use an internal micrometer and measure the diameter of this hole, if you do it at different locations, you get different measurements, but the size of the actual mating envelope for this hole is just one single number. Okay, and similarly for this one too, you can see again, you have different actual local measurements, but again, there is one size that is different than those probably for the actual mating envelope. And the important thing is it does not need to be horizontal. Okay, it can be tilted. As long as it's a perfect cylinder with maximum size that it could be, right, for a hole, is the actual cylinder with the maximum size that can pass through the hole, whether straight or whether at angle. Okay, so that is called the actual mating envelope for an internal feature. And here I highlighted them for you. So for internal feature is the perfect feature with largest size that can be inside that hole. For a shaft or an external, it's the perfect cylinder that can be inside, the shaft can fit inside it, but it's with minimum size. Okay, the last thing we have is a from and to symbol. In the past, I showed you a between symbol. So I had 2 points on a profile, and then I said, hey, between like M and N, we had something like this. Between M and N, I want the profile tolerance to be 0.1. So this thing I mentioned in one of my previous videos, the between symbol. But now you have something different. It's called a from to symbol. So here you say from M to N, I want the profile tolerance to change gradually from 0.1 to 0.2, and a direction is important because the first one is like one side of it, the other one is the other number, so you need to know in which direction it has to change. So here, if you look at it from M to N, this tolerance region is gradually changing from what it was here, 0.1, to now what is here, what, 0.2, it's gradually changing. So if you have a gradually changing profile, you're going to provide 2 numbers with a dash for the tolerance, for the profile tolerance, and 2 points, and then M to N. Okay, and if you want to do that in SolidWorks, let me show you how you do that. So here is SolidWorks, and I want to add that here. So I go with a note, and I add a note here at the start of this fillet and call it maybe M. Then come here and add another one and call it N in here, right? Like that. And then I go with a profile tolerance, put it on the surface, and say what? This is a profile tolerance, a surface profile, and it goes between 0.1 dash 0.2, and with respect to the 3 datums, A, B, and C. And then you have to add that between symbol. So you double click here and then click on this bottom part and say what? From to, and you say from M to what? N. Done. Okay, so this is how you add a from to symbol in GD&T. Okay, so hopefully this video was useful to you, and I'm going to see you in my next video. Thank you.